1204. Northern France. The fortress of Chateau Gaillard rises from limestone cliffs, its walls 12 feet thick, built by Richard the Lionheart to be impregnable. For 8 months, King Philip Augustus has laid siege to this stronghold. Mining has failed. Scaling has failed. Battering rams can't reach walls defended by murder holes and boiling oil. Then French engineers begin building something new. A machine 60 feet tall. A machine that will hurl 300-pound stones over 300 yards. A machine that will change warfare forever. They call it Cabulus, the beast that devours castles. How did medieval engineers build something this destructive using only rope, wood, and gravity? The trebuchet wasn't just another siege weapon. It was a revolution in applied physics. Before 1200, siege engines relied on human muscle power. Mangonels used crews of 50 men pulling ropes to bend wooden arms. They could throw smaller stones accurately, but lacked the kinetic energy to breach thick masonry. The innovation that changed everything was counterweight. Instead of human muscle, medieval engineers harnessed gravity itself. A massive weight falling just 15 feet could generate more consistent power than 100 men pulling ropes, and it never got tired. Contemporary chronicles describe Cabulus demolishing sections of Gaillard's walls with methodical precision. Each shot delivered roughly 200,000 joules of energy, enough force to crack mortar joints and dislodge ashlar blocks that had taken master masons years to fit. The psychological impact was devastating. Defenders who had never seen walls breached by artillery watched their supposedly impregnable fortress crumble stone by stone. Within weeks, Chateau Gaillard fell, and with it, the age of castle supremacy ended forever. To understand why Cabulus worked, we have to start with the physics. A trebuchet is fundamentally a lever, the same tool humans have used for millennia to multiply force. But this lever operates on a scale that transforms falling weight into projectile velocity through mechanical advantage. The key insight medieval engineers grasped was beam ratio. Cabulus used a throwing arm 54 feet long, with the pivot point positioned to create a 2-to-1 ratio, 36 feet of long arm to 18 feet of short arm. Modern engineers often assume longer ratios would be better, but medieval builders understood something crucial about their materials. Oak timber, even massive logs, has limits. A longer, thinner arm would snap under the shock loads generated by a 15-ton counterweight. The 2-to-1 ratio provided optimal balance between throwing power and structural survival. The real genius lies in the sling system, which creates what physicists call a double pendulum. As the counterweight drops and the beam rotates, the projectile doesn't immediately lift. It drags along a wooden trough, allowing the massive weight to build momentum. Then, as the beam approaches vertical, the sling whips around the arm tip, accelerating far faster than the beam itself. At the moment of release, the 300-pound stone is traveling over 120 miles per hour. The counterweight does what human muscle never could. It stores gravitational potential energy and releases it in a concentrated burst that converts falling motion into projectile velocity with devastating efficiency. Building a functional trebuchet using authentic medieval methods means respecting every material choice 13th century engineers made. We start with European oak, the only wood that combines the strength and flexibility required for this application. Oak has a modulus of rupture around 100 megapascals, meaning it can bend under enormous stress without breaking. Modern lumber yards sell kiln-dried oak, but medieval builders used air-seasoned timber, aged at least 1 year per inch of thickness to achieve maximum strength. The throwing arm requires a single log, 36 feet long, tapered from 12 inches at the axle to 8 inches at the tip. This taper isn't decorative. It reduces the moment of inertia, ensuring more energy transfers to the projectile rather than accelerating the wood itself. The frame construction follows principles any medieval carpenter would recognize. 2 massive triangular trestles, each 28 feet tall, connected by heavy cross-bracing. Every joint uses mortise and tenon construction, with oak pins driven through holes to lock the connections. The triangle is the only stable shape in structural engineering. It converts all loads into compression and tension, avoiding the bending moments that would snap timbers under the shock of firing. The counterweight hangs from a hinged connection, allowing it to fall more vertically than a fixed weight. This hinge extracts maximum work from gravity, while reducing the violent recoil that could destroy the frame after repeated shots. The axle represents the most critical stress point in the entire machine. 15 tons of counterweight creates bearing loads that would seize or ignite a dry wooden interface. Medieval engineers solved this with a combination of wrought iron and organic lubrication. The axle itself is wrought iron, not the brittle cast iron of later periods, but hammered iron with fibrous slag inclusions that resist fatigue failure. The bearing surfaces are lined with hardwood sleeves, typically elm, that can be replaced when worn. Continuous lubrication comes from tallow, rendered beef fat mixed with lime, to create a heat-resistant grease that medieval engineers knew would maintain lubricity under extreme pressure. The sling requires hemp cordage, not the synthetic ropes available today. Hemp has virtually no stretch, which is critical for energy transfer. Modern nylon or polypropylene rope would absorb energy like a spring, reducing projectile velocity and introducing unpredictable oscillations. We splice quarter-inch hemp line into a diamond mesh pouch that conforms to the projectile while shedding air resistance during the violent acceleration of the whip phase. The release mechanism appears simple, but requires precise adjustment. An iron pin driven through the arm tip controls exactly when the sling opens. The pin's angle determines trajectory. A 15-degree forward curve holds the sling longer, producing a flatter, wall-battering shot. Heating and bending this pin allows fine-tuning for different ranges and targets. Raising the frame requires the same mechanical advantage principles that power the trebuchet itself. Medieval engineers used shear legs, temporary crane systems made from 2 oak poles lashed at the top. Block and tackle pulleys multiply human effort, allowing a crew of 12 men to lift multi-ton frame sections into position. Assembly follows a precise sequence. The triangular sides are built flat on the ground, then raised simultaneously and locked into position, with cross-bracing. The throwing arm, weighing nearly a ton, requires careful placement on iron gudgeons that allow smooth rotation. Every measurement matters. The counterweight box, called a hooch in medieval French, must hang exactly 12 feet below the axle when the arm is horizontal. This distance determines how much gravitational potential energy the system stores. We fill the box with local stone, achieving the density of roughly 1,600 kilograms per cubic meter that provides the optimal mass ratio for 300-pound projectiles. The moment of truth arrives with spanning. Loading the weapon for firing, the counterweight must be raised against gravity using windlass systems mounted at the front of the frame. Steel cables run through multiple pulleys, creating mechanical advantage that reduces the effective load from 30,000 pounds to roughly 500. A crew of 10 men can span the weapon in approximately 12 minutes, storing enough potential energy to launch a projectile over a quarter mile. The trigger mechanism holds this enormous force with a simple slip hook, an iron catch that wants to release but is held by a safety pin. When the master engineer strikes that pin with a hammer, physics takes over. 15 tons of counterweight drops. The massive oak beam accelerates upward. The sling whips forward. In less than 3 seconds, gravitational potential energy becomes projectile kinetic energy with mechanical efficiency that rivals modern artillery. Our test proves the engineering works exactly as medieval chronicles claimed. The scale model, built to identical proportions, but sized for a 3-pound projectile instead of 300 pounds, demonstrates the physics principles that made Cabulus so devastating. The counterweight drops. The beam snaps through its arc. The sling releases with perfect timing. The projectile arcs through space and impacts exactly 100 yards downrange, validating every calculation about mechanical advantage, energy transfer, and structural loading that 13th century engineers understood intuitively. The forces scale perfectly. If our model can throw 3 pounds 100 yards, the full-size Cabulus could indeed throw 300 pounds 300 yards with the impact energy to shatter castle walls. No computers, no mathematical equations, no industrial materials, just empirical knowledge refined over generations by engineers who understood leverage, stress distribution, and energy conversion better than most modern builders. Medieval craftsmen couldn't calculate moment arms or angular momentum, but they grasped these principles through hands-on experience with forces and materials. Cabulus represents the pinnacle of mechanical engineering before the Industrial Revolution. Maximum power multiplication using only organic materials and gravitational energy. The machine that demolished Chateau Gaillard proved that human ingenuity, applied systematically, could harness natural forces to change the course of history. Good engineering doesn't require advanced technology. It requires understanding how the world works